Have you ever thought about how a computer works? How does it do complex mathematics or run complicated programs? Well, it all starts with digital logic design. If you think of any digital device you own, it has some level of logic built into it. And somebody really smart had to design that. Digital logic is all around us, and it shapes the world we live in today. But before we get too deep, I think it would be a good idea to take a step back and explain what digital logic really is. First, digital. Now, you've probably heard this word a lot, but what does it really mean? Well, there's two main types of signals, digital and analog. Analog signals can take on any value across a continuous range. Measurements like voltage, current, weight, height, these are all analog values. A digital signal, on the other hand, can only have a value of either 0 or 1 at any point in time. It can't have any other value. Things like light switches or push buttons, these would be represented as digital values. They can only be a 0 or a 1. Think off or on, low or high, false or true. These are all ways that we can describe a digital value. Digital computers are only able to work with digital signals in order to do their job. But what if we need to use an analog value with a digital computer? We can actually represent analog values with an equivalent digital representation. Wait, how do we do that? Well, we can't jump straight to the good stuff without covering the basics first. Besides, that's more of a deep dive for the next video. Let's get back to digital signals so we can really understand what's going on. There's a ton of examples of systems that used to be analog but have become digitized. Photographs are a great example of this. Photographs used to be created using chemical processes to capture an image, but now they've all become digital. They're made up of an array of pixels, like 1920 by 1080. And each pixel has a red, a green, and a blue value, typically expressed in at least 8 bits each. So each bit is a digital value that can only be a 0 or a 1. A simple 1920 by 1080 image could be as large as nearly 50 million bits. And that's a lot of information. Videos are another great example of an old analog technology that's now become digital. Instead of videos being captured on tape with audio and video tracks, now they're captured digitally and then encoded and either written to a disk or just streamed over the internet. That's something that would be impossible with analog media. One last example is a carburetor. Most vehicles used to use a carburetor to control the amount of air and fuel going to their engine. And carburetors had to be tuned using set screws and were controlled with complex mechanical linkages. But nowadays, almost all of the cars you see on the road are using something called fuel injection. This is where a small computer in the car calculates the exact amount of fuel that should be going to the engine based on several inputs. And there's tons of other examples of devices or systems that used to be completely analog that are now digital. But why? Why is everything going digital? Well, there's several reasons, but here are some of the top ones. The first would be reliability, or think of it as reproducibility. While those carburetors did a great job most of the time, on cold mornings you would have to manually choke the carburetor, which adjusts the air-fuel ratio so that the engine can start properly. And those VHS tapes that we used to collect could only be watched so many times before the footage started to become grainy or staticky. Or think of vinyl records. Over time, they would degrade and the audio would become less crisp, or the needle would wear down. You don't run into these problems with digital systems because in a digital system, given the same set of inputs, we can reliably determine what the output's going to be. Another reason everything is going digital is the flexibility or functionality. Digital systems can be simplified or reduced to their most basic forms and then represented in the real world or programmatically using logic gates. Which brings me to the last reason I think everything is becoming digitized, and that is the programmability of digital systems. We're all familiar with computers and how you can write code to accomplish very complex tasks. Well, you can use the same embedded processing hardware in tons of different devices and just change the program running on it. This makes digital systems very versatile and much cheaper to reproduce. So, digital systems are great, but how do we start designing them? Well, like with anything, we have to start with the basics. And the most basic digital devices are called gates. And no, they're not named after this guy. They're called gates because they control or gate the flow of digital information. The three most basic and most important gates are the AND gate, the OR gate, and the NOT gate. With these three gates, we can recreate virtually any digital system in existence. Now, granted, we may need a lot of them, like a whole lot of them, but we can do it. We represent how these gates work using a tool called a truth table. And by the way, you're definitely going to be seeing these again. Truth tables take our inputs on the left side and tell us what the output on the right side will be based on the combination of inputs. Because of this, a gate is called a combinational circuit, since its output depends only on the current combination of its input values. Let's take a closer look at the AND gate. This particular AND gate has two inputs, and every AND gate has only one output. If input 1 is a 0 and input 2 is a 0, well then our output is 0, because 0 and 0 makes 0. Well, that makes sense. What if input 1 is a 0, but input 2 is a 1? Well, then our output is still a 0. This is because an AND gate requires both inputs to be true for the output to be true. Let's keep going. What if input 1 is a 1 and input 2 is a 0? Like we saw with the last table entry, both inputs have to be true in order for the output to also be true, or a 1. So our output in this case is still going to be a 0. And the last case would be where both input 1 and input 2 are 1s. In this case, our output would be a 1, because 1 and 1 makes a 1. That's why it's called an AND gate, because both inputs have to be true for the output to be true. How about the OR gate? OR gates don't require all of its inputs to be true for the output to be true like an AND gate does. OR gates only require one input to be true for the output to be true. Let's take a look at that. For an OR gate, if input 1 is a 0 and input 2 is a 0, our output is a 0. This is because none of our inputs are currently true. If input 1 is a 0, but input 2 is a 1, then we have at least one input that's currently true. This makes our output true. So our output here would be a 1. What about when input 1 is a 1 and input 2 is a 0? Well, there's no difference between this case and the previous one. At least one input has a value of 1, making our output also have a value of 1. And the last case would be where both inputs are 1. In this case, our output would also be a 1. This is because for an OR gate, the requirement for the output to be 1 is for at least one input to be a 1. If both inputs are 1, then that still satisfies the requirement. Now, there is another type of OR gate called an exclusive OR gate. This gate functions exactly like an OR gate, but it requires exactly one input to be a 1 for the output to be a 1. This means that if input 1 and input 2 are both 1, then the output would be a 0. This is only true for an exclusive OR gate, not a regular OR gate. For a regular OR gate, if both inputs are true, then the output is also true. And lastly, the simplest gate of all, would be the simple NOT gate. This gate is also called an inverter because that's exactly what it does. The NOT gate has only one input and only one output, and the output is going to be the opposite of whatever the input is. If the input is a 0, then the output's a 1. If the input is a 1, then the output's a 0. There are more complicated digital devices, such as flip-flops and latches, but these are made up of a collection of gates. Flip-flops and latches store a state, which can typically only be changed at certain times, determined by a clock input or a reset input. A digital circuit that contains flip-flops or latches is called a sequential circuit. This is because its output at any point in time depends not only on its current inputs, but also on the past sequence of inputs. In other words, a sequential circuit has memory. You can use combinational and sequential circuit elements together to create a much more complex system containing more advanced logic. This is all great, but we live in an analog world, and we're powering these circuits with analog signals like voltage and current. So how do we turn that analog signal into a digital signal? Well, here's an example of an input to a microcontroller. The value of the input depends on the amount of voltage at the input. That voltage can be anywhere between 0 and 5 volts. We know for sure that 0 volts would mean the input is low, and 5 volts would mean the input is high. But what about the voltages between? Is 1 volt low or high? What about 3 volts? This is where specification sheets, or spec sheets, also called data sheets, come in handy. Every device manufacturer publishes specs, which describe the proper operating conditions for their device to operate as intended. Let's take a look at an example of a spec sheet. Here we can see this data sheet for a dual 2-input positive AND gate. This is just a chip with two 2-input AND gates built in. We can see from the data sheet that we need to power this chip with a voltage somewhere between 1.65 and 5.5 volts. Based on the voltage level used to power this chip, we can determine the required voltage level for a high input. We can see that if we power this chip with 5 volts, then we need at least 0.7 times that to register a high input, which would be 3.5 volts. But if we notice the voltage required to register a low input, it's 0.3 times our supply voltage of 5 volts, which is 1.5 volts. So if anything 3.5 volts and above is high, and anything 1.5 volts and below is low, what about that space between 1.5 and 3.5 volts? Well, anything in this range is going to be an invalid input, which could make our output unpredictable. This is why we use pull-up and pull-down resistors, so we don't have any undesired floating voltages. I'm going to dive deeper into pull-up and pull-down resistors in a future video, but for right now, I just want to cover the basics of how this digital logic works. Now, notice this chip has 2 AND gates built into it. A collection of 1 or more gates fabricated onto a single silicon chip is called an integrated circuit, or IC. Here's some examples of basic ICs. They can be made up of AND gates, OR gates, NAND gates, NOR gates, NOT gates, latches, flip-flops, or they can be made up of some special circuitry for a specific purpose. If you open any electronic component, you will find ICs. They can range from as little as 1 gate on a chip to trillions of gates, normally called transistors, on a single chip. ICs that have a specific application or are designed for a particular purpose are called application-specific ICs, also known as ASICs. Some examples of ASICs could include lithium-ion battery charge controllers or DVD player chips. ICs are mounted onto printed circuit boards, or PCBs, which have tiny conductive wire-like connections called traces embedded into the board, which connects different components to each other. This is how every digital device you interact with works. From your microwave to your car to your phone, every digital device has at least one PCB with at least one IC, oftentimes with thousands, millions, or more transistors operating as logic gates. In the next video, we'll look at the numbering systems required to turn our analog world into digital and learn to use numbers like a computer. I'll see you next time.